Assignment 4.5, part 2. So, presenting data. So, here's a histogram. A histogram is used to show different values um, for a certain set of data. So, I've got the standing vertical jump in centimetres here. It also goes upon frequency and a grouping. So, it separated my data out into groupings of 20. So, because I've got values from 15 to 75, and it's got the first group of 15 to 35, second group of 35 to 55, and a third group of 55 to 75. This tells you how many values were in a certain amount of that group. So 5 values were in the first group, 8 in the second, and 1 in the final group. It's just another way of showing the frequency of a certain set of data. Next we have box plots. So a box plot can be used again to show something about the set of data. So the lines at the top, which are the whiskers, these are considered to be the standard deviation. So this is said these values could lie between this and that. The line in the middle is the upper quartile, and below that is the lower. And the X in the middle, that is the mean. So this is the value that it should be. Conveniently, it lies in the middle of the data set, so it could also be the median. A box and whisker graph is very useful. However, when you have many different sets of data, it can become very confusing and hard to interpret. These graphs can also look very spread out when done on computer if there are many different sets of data that aren't in the same bracket of scores. So when you use these, you have to be careful with the set of score that you use. So, normal distribution. So the normal distribution follows a certain style, usually bell-shaped, and the center point should be 0. This is what a normal distribution curve should look like, with data around it. So as you can see, you have the curve here, and then you've got the data sets above it. The normal distribution predicts the data set, and you could say that this data is normally distributed due to the curvature that it should take. So there are different things that can happen. So if the data is skewed, so you can have a negative skew or a positive skew. And this can happen when the data isn't right, or you haven't worked something out correctly. And all that happens is the data is moved either to the left, to the right if it's negative, or to the left if it's positive, and that's the bell that moves. So there isn't an even spread from this side of the negative skew to this side. More of the data is towards this right side. Whereas if we go back and show you normal distribution, you can see that this data is evenly spread on both sides. So, outliers. Outliers can impact the data set dramatically, and this is because you could say on the data that I've got here, there is a weak positive correlation down the bottom. However, this one outlier that I've highlighted in red and given it a glow, you can say that's an outlier. This is because it is significantly different to the other values. The next highest value is 14, and that value is 20. There is a 6 gap difference between that point and that point. However, you could say that that point there is 3 and that point there is 14, and there's an 11 difference there. But the data around it, so this data that I'm highlighting here, this data here will help that, because even though they're the extremes, that's the top value and that's the lowest value, that would be the range. But the values in the middle are what stop that higher value from being an outlier. Outliers can impact results because the range for this would now be 17, and there are no values that are above 15. So the outlier can impact things such as the range, the mode, and the median. Trimming and windsoring. Trimming is where you're getting rid of the numbers that you believe are irrelevant towards your findings, and windsoring is where you change the value of an outlier to the next nearest value. So, trimming. So here you can see that I've got on the left-hand side in red skin fold caliper measures for biceps and triceps in rank order distribution, and on the right I've got skin fold caliper tests, but this has been trimmed. So the one on the left has quite a few sets of data, going from for biceps going from 2 to 63 and triceps 1 to 56. I have decided to trim values on the for biceps from 63 through to 20. Those 4 values there gone, and then for biceps 56 through 20, so those 4 values there also gone. I did this because there was a massive difference between 13 and 23, and 12 to 20 compared to the other result. When trimming, you must look at the other results and say whether you believe that there is a significant difference between them or not. If this value is very large, then there's a big difference. I would recommend that you trim. Windsoring. Windsoring is where you change the value to make it fit your data. So as you can see, I've got my value of 20 on my left graph here. I then change that value to 13. I change that value because it helps the data set and doesn't impact other things such as the range, the mode, the medium. Windsoring is a useful way of ensuring that your data stays accurate but also true. Because if you had a point that was 50 and your next point was 12, you'd want to change that, or you want to windsor it, or possibly even trim it. Trimming and windsoring are a very good way of stopping anomalies occurring. So, point 3, standard deviation. So the standard deviation indicates how much of values in the distribution can deviate from the mean of the distribution. So on the left here, you've got the table. So this table has the participants, their score. You then use the score minus the mean. So I've calculated the mean to the bottom, and the score of that was 47.43. And you score minus the mean, and then the total of that, which is what you do, you score minus the mean squared. So you square minus 6.43, you get you 41.34, and so forth down the rest of the table. The total of that gives you 907.36. The equation used to calculate the standard deviation is the standard deviation equals the root of sum of x minus m squared, and m is the mean. And then over n minus 1, so n is the number minus 1. So the mean is 664 over 14. That's because it's a total of 41 through to 42 all added together. That gives you 40, and then over 14 because the values we have. That gives you 47.43. Then put that into the standard deviation. So the standard deviation equals 907.36 over 13. That's because it's x minus m squared. So it's it's this column on the right here that you just put into that there. Over 13 gives you 8.35, and that would be the standard deviation for this set of data. Distribution curve. So there are many different ways that a distribution curve can occur. So standard deviation for this higher one here is 7, whereas the standard deviation is 12. So when the data is more condensed and there is a higher bell on the curve, the standard deviation is going to be considerably lower. But when the data is more spread out, the deviation becomes higher. So yeah, just here, as I was saying earlier, there's a small standard deviation, whereas there's a large standard deviation. You would prefer a smaller standard deviation as there is less chance for results to change. There are different ways of describing levels of measurement. So as you can see in the table here, you've got types of descriptive statistics. They're nominal, ordinal, interval, and ratio, and mode, count, and then they're the levels of measurement. And then the types of descriptive statistics are mode, counts, frequency, median, minimum, maximum, range, mean, variance, standard deviation. So as you can see, the nominal does the mode, but not the median or mean. The ordinal does all these first two, but not the last one. Interval does all of them, and ratio does all of them. And this is a benefit. Part 4. Pearson statistical tests. So the equation used to calculate Pearson's statistical test is this up here. And then you have your data here. So you put in all your participants and you work out the number. So the number of them, so that's 8. You then have all their scores. So X is their first score. You then put that in. You total up X. You then also square X. You need to square X because you need to work out what X squared is and Y squared is here. You then square X again, but you square the sum. In this first one, you square the sum of X. So you square 58. Whereas here, you square 5, 5, 5, and so on. You then get a second set of data from the participants, and then you do exactly the same thing. So you total it all up, and then you square that answer there. So that's 55 squared, gives you 3,025, and then you square it again normally. You then times X and Y together. So you times 5 by 6, 5 by 7, 5 by 3, and so on. You then total that number up. You then move along onto the table here. You can say, do you see n? So that needs to be 8 times the sum of x, y. So, but that's not x, y, it's x times y. So it's 58 times, ignore me. That's 87 plus 58, 55, and then you do that. You then use your other data down from there into this next column here, and so forth. You can follow the equation all the way through to give you a calculated value, R value of 62.26, wrong, and then you follow down in the table to n minus 2, which is 6. So look onto 6. You want the level of significance is 0.5, and the answer is 0.767067. So you could say that there is a significant difference because it's larger. Spearman's rank order. So the equation for Spearman's rank order is RS equals 1 minus 6 times the sum of d squared over n open bracket n squared minus 1 close bracket. As again, I have my data here. You need to work out the number, so 10, and then that squared, which is 100. Oh, sorry. And then you need to work out the difference between the rank. So you have to rank them all. So I've ranked them here, smaller, and then I've ranked them here again. You work out the difference, and then the difference between the rank squared. So you then put your data in. So you do 6 times 118, because that is the difference rank squared, over 10, open bracket 10 squared minus 1. So you get 708 over 990, which gives you a calculated R value, and then you do 1 minus 0.715, which gives you a calculated R value of 0.284. And you then work along, so you go n minus 2 is 8, so you go there to 0.5, 0.76. Then you say if the calculated value is larger than the critical value, then there is significant difference. However, mine is smaller, so there is not a significant difference. Dependent t-test. So the equation used for the dependent t-test is ED over the root of n of the sum of d squared minus d squared, and then n minus 1 over n minus 1. So I've worked out how many participants I have over here, their total score for the freestanding vertical jump, their total score for the post, the difference, and then the difference squared. So, where am I? Yeah, so the sum of D. So the sum of D, difference is 72. And then I do 6 times 1,106 minus 72 squared, 6, and then over 6 minus 1. That gives me 72 over 6,636 minus 5,184 over 5. 72, then that goes 72 over 1,452 over 5. And then I go 72 over 290.4 square root that, and it gives you your calculated t-value of 17.04. And I can say that there is a significant difference if I go down the table and work it out. Independent t-test. So the final test is the independent t-test. This is where you use m-1, m1 minus m2 over sd1 squared over m1 plus sd2 squared over n2. So I've worked out my standard deviation for all of my results, and the mean for those results works out the mean for the second one, the standard deviation. From this, I put my data in, so my mean is 1.67, 1.88, 1.020, squared, 0.87 squared over 10 for both of those. I add those together as well at the end. I then work out I have 0.12 on the top over 0.04 over 10 plus 0.76 over 10. I then get 0.12 over 0.04 plus 0.076, which gives me minus 0.12 over 2.8, and I divide that and get minus 0.43. I go along my table and I can work out that there is no significant difference. Thank you very much.